Suppose in a roulette game, a player has 50-50 chance of winning or losing. He is able to place any bet before each game, and he will win or lose this amount of money depending on the result of the game. Suppose further that there exists a source of money that is willing to lend him any amounts as long as the player promises to pay back. Then, with no further assumption, the player is guaranteed to make money. This seems counterintuitive, but it's indeed true. Let's look at the following strategy that always ends up with the player winning $1. So to begin with, the player bets $1 for the first game. If he wins the game, easy, he's got what he wanted. He stops. If he loses, he has a net loss of $1, so he needs to win $2 to reach his goal. Then he simply bets $2 for the next game. Again, if he wins, he stops. If he loses again, he has a net loss of $3. So he bets $4 for the next game. This process continues until he wins the first game, after which he has a net income of $1. Since every single game is independent, and each game he only has 50% chance of losing, the probability of him never winning is essentially zero. Since there's a source of money that is willing to lend him any amount, he never has to worry about running out of money before winning. So he always gets that $1. Since this process is repeatable, he can repeat this process and become a billionaire. How can a seemingly fair game end up being so much in favor for the player? Let's put aside this question about the roulette game first and discuss two insightful concepts: arbitrage and martingale. People often use the phrase, "there is no free lunch," to describe the no arbitrage assumption in our market. But arbitrage isn't exactly equivalent to free lunch. More precisely, an arbitrage is a strict positive chance of having free lunch. In technical terms, an arbitrage is a portfolio value process xt satisfying x not equal to 0, and for some capital T greater than 0, the probability of x capital T being negative is strictly 0, while the probability of x capital T being positive is greater than 0. Decomposing these probabilistic equations, the definition of arbitrage is actually simple. We trade according to some method or algorithm and for a certain duration. And in the end, if we're guaranteed to not lose any money or having a strict positive chance of earning money, then we call this unfair advantage an arbitrage. The second key concept is martingale. For the purpose of discussing the roulette game, we simply think of a martingale as a portfolio process xt that has no tendency to rise or fall. This doesn't mean the process stays constant in value, but rather the process stays constant in expectation. As an example, let's look at this roulette game and verify that it is indeed a martingale. Suppose a player keeps on playing the game, winning or losing money, and thus generating a portfolio process. At any point of the process, the player can bet delta dollars for the next game. Thus, following the rules of the game, we see the process could either increment by delta or decrement by delta, both with equal probability. Then we say the process stays constant in expectation because the game neither favors the player nor the host, while the wealth of the player is neither more likely to increase nor more likely to decrease. The first fundamental theorem of asset pricing links these two concepts together. It states, if a market model has a risk-neutral probability measure, then it does not admit arbitrage. For the purpose of discussing the roulette game, we simplify the theorem as martingale structures imply no arbitrage. Since we have proven the martingale structure of the roulette game, we get no arbitrage assumption about the game. In other words, no one is guaranteed to make money out of this game. But our previous demonstration apparently illustrated otherwise. So, is our theorem broken?